Welcome to the deep dive. This is where we take, those massive stacks of documentation, architectural mandates, security research, the stuff that usually just sits there until, well, something breaks,
Yeah.
and we pull out the practical operational knowledge you actually need.
And today we are really getting foundational. It's a true deep dive into the global services that, let's be honest, underpin pretty much every significant modern application out there. We're talking AWS Elastic Load Balancing, Route 53 for DNS, and CloudFront, the CDN.
Yeah, and our source material for this one is not just a few blog posts. It's this huge, comprehensive master document. It lays out the blueprints, the mandatory security controls, and importantly, some of the really painful lessons learned from years of, well, availability incidents and security scares. So our mission today isn't just defining these things. We want to give you the essential playbook. You need to understand the critical security controls, the resilience trade-offs you have to make when you're operating big, high-scale applications on this global AWS stack. We're trying to get past the what and really dig into the how and the why.
Yeah.
Certain configurations aren't just suggestions, they're basically mandates.
And you absolutely cannot talk about any of this without grounding it firmly in the shared responsibility model, the SRM. It's fundamental. It clearly defines who's responsible for what. And honestly, it's probably the single most important concept governing how you configure anything in the cloud.
Right.
AWS takes care of the security of the cloud.
Okay, so unpack that a bit. What does security of the cloud actually mean when we're talking about ELB Route 53 CloudFront?
It means the underlying plumbing, essentially. For ELB, think about the hyperplane architecture, that massively scalable, automatically managed backend. For Route 53, it's the global Anycast network, the data plane that answers DNS queries everywhere. It's the physical security of the data centers, the hardware, the hypervisors. AWS builds, manages, and protects all of that global infrastructure.
The second we log into the AWS console, right?
Right.
And we start clicking around, configuring listeners, setting up health checks, defining access policies.
That's the line. You've just crossed into security in the cloud, and our sources, they make this incredibly clear. This is where most of the failures happen. The architectural missteps, the security vulnerabilities, they usually originate from the customer's configuration, no matter how solid that underlying AWS infrastructure is.
Yeah, it's on us then.
It's entirely on you. Your responsibility covers that configuration management piece, and the devil is absolutely in the details there. We're talking about setting up those really granular wave rules, configuring origin access control or OAC correctly for CloudFront, writing smart health check logic. It's enforcing multi-factor authentication, MFA, on those super critical IAM users. It's ensuring complete data protection, making sure TLS is enforced rigorously everywhere.
This one control.
And the whole thing can unravel. The global infrastructure can't magically compensate for a configuration mistake you made.
Okay, that sets the stage perfectly. So
Yeah.
let's unpack this, starting with, I guess, the regional frontline worker, the application load balancer.
Right. The application load balancer, or ALB. It's your gatekeeper at layer 7, the application layer of the OSI model. And that's its key architectural feature, what really sets it apart. Unlike, say, a network load balancer, an NLB, which just looks at IPs and ports layer 4 stuff, the ALB does deep packet inspection. It looks inside the request.
Okay, so layer 7 inspection. But there's always a trade-off, isn't there? What do we give up when we choose that smarter layer 7 ALB over the, maybe simpler, faster layer 4 NLB?
It really comes down to latency versus intelligence. NLBs are incredibly fast. They handle raw TCP/UDP traffic at enormous scale with super low latency, precisely because they don't peek inside the packets. The ALB introduces a tiny bit more latency. We're talking microseconds, usually, because it has to inspect that content. It needs to see the host header, the URL path, maybe specific query strings, the HTTP method.
But that intelligence is what gives it its power, right?
Exactly. That's where the value is. That instruction allows for really sophisticated traffic manipulation and routing.
Which brings us to the listener rules. This is where you define that logic. You can set up this whole hierarchy of rules to manage traffic flow. Like, maybe all requests from mysite.com for my site competency go to this set of servers, but mysite.com images go somewhere completely different, maybe even using a different internal protocol.
Absolutely. The listener evaluates rules in priority order based on conditions you set: path, host, headers, method, source IP, query strings. If no rule matches, it hits the default rule, which usually distributes traffic using a round-robin algorithm across the healthy targets in your target group.
Usually round robin, but you mentioned options.
Yeah, for certain workloads, maybe where requests have very different processing times, you might switch the algorithm to least outstanding requests.
Uh,
The ALB then tries to send each new request to the target that's currently handling the fewest active connections. It can help smooth things out, prevent one server from getting overloaded while others are idle.
okay, makes sense. Now let's talk security posture. The mandates, starting with encryption rights, centralizing it.
Correct. This is non-negotiable, really. The first architectural best practice our sources hammer home is mandatory protocol redirection. Any public-facing service, you must configure the ALB listener to automatically take any incoming HTTP request on port 80 and force it to redirect to HTTPS on port 443.
So the ALB itself becomes the enforcer. It sees an insecure request and basically says, nope, go back and come again securely over HTTPS.
Exactly.
Which means the back-end application servers, they never even have to see plain HTTP traffic.
Right. It centralizes that enforcement point and dramatically simplifies the security configuration of your back-end targets. They only need to listen on HTTPS. And tightly coupled with this is certificate management. The sources are prescriptive here. Mandatory use of AWS Certificate Manager, ACM.
Why ACM specifically?
Well, it integrates seamlessly with ALB, obviously. It handles provisioning the TLS certificates. Crucially, it automates the renewal process, which is often error-prone if done manually. And maybe most importantly, it securely manages the private keys associated with those certificates. You don't have keys lying around on servers. ACM handles it.
Okay, so we've secured the front door connection from the client to the ALB,
Yeah.
but that's only half the story. We need end-to-end encryption, right?
Absolutely vital, especially if you're dealing with sensitive data or strict compliance regimes. You must configure the target group, the connection from the ALB to your backend targets, to also use HTTP STLS, not plain HTTP.
Even though that traffic is typically inside my own private VPC, why is encrypting internal traffic so critical?
Defense in depth. It guards against potential risks inside your VPC, maybe a compromised instance trying to sniff traffic, or some other unforeseen internal man-in-the-middle scenario. It aligns with zero trust principles. Don't assume internal network segments are inherently safe. Plus, you need to be constantly auditing and enforcing strong TLS policies on the ALB itself.
Because old TLS versions are vulnerable.
Exactly. We know from past incidents that older policies allowed weak ciphers or vulnerable protocol versions like TLS 1.0, 1.1. You have to deprecate those immediately, mandate a minimum of TLS 1.2, and really you should be using policies that prioritize TLS 1.3 wherever possible.
TLS 1.3 is faster and removes a lot of the old insecure cipher cruft, right?
Precisely. Faster handshakes, fewer legacy options, inherently more secure. Using those modern TLS 1.3 security policies on the listener helps prevent downgrade attacks, where an attacker tricks the client and ALB into negotiating a weaker encryption standard. The ALB security policy controls that entire negotiation.
Okay, shifting gears slightly. Modern apps use modern protocols. The sources mention ALB is built for things like HTTP2 and gRPC.
Yeah, it's not just an old HTTP 1.1 handler. HTTP 2 offers big performance benefits, multiplexing, header compression, and ALB supports it natively. And gRPC, Google's RPC framework, is huge for microservices communication. ALB understands gRPC, lets you route based on gRPC methods, handles the underlying HTTP 2 transport correctly. It's engineered for these newer workloads.
What about things that need persistent connections, like WebSockets for real-time features?
Handled natively, too. The ALB facilitates the initial HTTP 1.1 upgrade request to establish the WebSocket connection, WLOS or WSS. Once established, the ALB maintains that persistent, stateful connection between the client and the specific target server that handled the upgrade. Crucial for chat apps, live data feeds, that sort of thing.
Got it. Let's circle back quickly to those listener rules. We talked about forwarding traffic to targets, but what about the actions that don't forward? They seem powerful.
They really are. The fixed response action is great. You can configure the ALB itself to just return a static response, maybe a down for maintenance page with a 503 status code, or an immediate access denied with a 403 without ever sending the request to a backend target.
Useful for handling specific paths or error conditions cleanly.
Exactly. And the redirect action gives you fine-grained control over sending back permanent 301 or temporary 302 redirects based on request characteristics, different hosts, paths, query strings.
And the authentication piece you mentioned earlier.
Yeah.
Authentication has action. That sounds like it could simplify application code quite a bit.
It's a major feature, especially for HTTPS listeners. You can configure actions like authenticate cognito or authenticate OIDI. The ALB itself handles the entire authentication flow, redirecting the user to your identity provider, like Cognito or maybe Okta or Auth0 via OIDC, handling the token exchange, validating the session.
And then it passes the user's identity information to the backend.
Right. Once the user's authenticated, the ALB forwards the request to the target, but it adds signed HTTP headers containing the user's claims from the identity token. Your application code just needs to trust and parse those headers rather than implementing the whole complex OIDC or SAML dance itself. It decouples identity verification from your core application logic.
That sounds incredibly useful. Any gotchas with that?
There is one slightly obscure but critical technical detail we found to mention. When the ALB is acting as an OIDC client using Authenticate OIDCO, it currently only supports making the outbound connections to your IDP's token and user info endpoints using IPv4.
Ah. So if my IDP or my internal network setup relies heavily on IPv6,
You could run into trouble. You'd need to ensure there's a translation mechanism, like a NAT gateway, that allows the ALB's IPv4-only OIDC client traffic to reach your IDP successfully. It's a small point, but could definitely trip you up during deployment if you weren't aware of it.
that's exactly the kind of detail we do these deep dives for. Okay, so we've secured the regional application layer, but none of that matters if the global entry point, the DNS layer, isn't absolutely rock solid. Which brings us to Route 53. Here's where it gets really interesting, shifting from regional traffic management to global resilience with DNS.
Exactly. Route 53 is it's the central nervous system for your global traffic flow. Architecturally, its defining feature is that it's a massively scalable DNS service built on any CAS networking. It's deployed across, I think it's over 200 points of presence, puppies, globally now.
Anycast, people hear that term a lot. What does it actually mean for resilience day to day?
Anycast means AWS advertises the same IP addresses for the Route 53 DNS servers from all those POPs simultaneously. So when your browser, or any client, sends a DNS query for your domain, the Internet's routing system, BGP, automatically directs that query to the geographically closest Route 53 POP that's advertising those IPs.
So it's inherently finding the nearest available entry point if a POP in, say, Frankfurt has a problem.
Your query just gets routed to the next nearest healthy POP, maybe Paris, maybe Amsterdam automatically. There's no configuration change needed on your end. This is why the data plane of Route 53, the part that actually answers the DNS queries and runs the health checks, is so incredibly resilient.
Okay, data plane. Globally resilient thanks to Anycast. But you always have to distinguish that from the control plane.
Always.
Yeah.
The control plane is where you make changes. When you go into the console or use the API to add a new DNS record, modify a health check, change delegation, that's the control plane. And historically, for many AWS services, the primary control plane infrastructure is hosted in a specific region, often S East 1.
That separation sounds good on paper. Protect the query answering part from the configuration part. But the sources point to a really significant historical incident, this control plane dependency crisis, that shows the danger here.
This is probably one of the most critical lessons in modern resilience engineering. There was a major outage where a company's disaster recovery plan fundamentally relied on being able to dynamically update Route 53 records during a failure event. Their playbook literally said, if region A fails, run this script to call the change resource record sets API and point traffic to region B.
Okay. But the failure event impacted the very region where the Route 53 control plane API was hosted.
Exactly. The API they needed to execute the failover was unavailable precisely because of the regional impairment they were trying to recover from. The API call failed. Traffic couldn't be redirected. The outage dragged on much, much longer than it should have, purely because the recovery strategy depended on a dynamic change via the control plane during the crisis itself.
That's terrifying. You have the plan, you know the fix, but the tool to apply the fix is broken too.
It led directly to what the sources call a mandatory rule for resilience engineering. Disaster recovery must be statically stable.
Statically stable, meaning no live API calls in an emergency.
Correct. Avoid dynamic API calls to critical services like Route 53 during a failure scenario. Your recovery mechanism must rely entirely on pre-provisioned configurations and the globally resilient data plane to execute the failover.
How does that work in practice then?
Think about using AWS Application Recovery Controller, ARC, routing controls. You pre-configure your DNS records, maybe using weighted routing or failover records, and associate them with Route 53 health checks, which are tied to these ARC routing controls. During a disaster, you don't call the Route 53 API. Instead, you make a much simpler, highly available API call to ARC to flip the state of a routing control.
Ah, so ARC tells Route 53's data plane this health check is now considered unhealthy.
Right. And the globally distributed Route 53 data plane sees that health check status change almost immediately and automatically starts routing traffic according to the predefined failover logic in your DNS records. No change resource record sets call needed during the critical window. That's static stability.
That makes Route 53 health checks absolutely foundational for any kind of reliable DR, especially when tied to regional endpoints like ALBs.
They are the core trigger mechanism. Once you have those static records set up, you use the different routing types to manage the flow based on health. We talked about latency-based routing, LBR for performance, directing users to the region with the lowest latency for them.
And weighted routing for things like canary releases or balancing load across regions.
Exactly. Sending, say, 10% of traffic to a new region initially, then gradually increasing the weight. And of course, failover routing is the classic active-passive setup, relying purely on health check status to switch traffic from a primary endpoint to a secondary one if the primary fails.
Okay, so the internal configuration and resilience patterns are critical. But DNS is also vulnerable to external attacks, things happening outside our AWS account, right? Like routing hijacks.
Absolutely. The sources specifically call out the BGP DNS hijack that hit my other wallet back in April 2018. That wasn't an AWS failure internally. It was an attack at the Internet Routing Layer Border Gateway Protocol, BGP. Malicious actors managed to advertise routes that effectively redirected DNS queries meant for Route 53 name servers serving the MyEtherWallet domain.
So traffic trying to resolve their domain got sent to attacker-controlled DNS searchers instead.
Yes, which then served fake IP addresses pointing to phishing sites designed to steal cryptocurrency keys. It's a stark reminder that even with perfect AWS configuration, you're still reliant on the integrity of global internet routing.
What's the lesson there, just so BGP stays stable?
Well, it highlights the need for robust external monitoring, things like DNS SEC, if applicable, though Route 53 handles much of this implicitly, and being aware of these potential BGP-level threats. But perhaps more directly controllable is the internal security dimension, DNS hijacking or domain takeover via IAM compromise.
And this usually comes down to human error or lack of basic security hygiene.
Almost always, according to the sources. Major compromises have been traced back simply to the lack of multi-factor authentication, MFA, on a privileged IAM user account. If an attacker gets credentials for an IAM user that has permissions to change your Route 53 hosted zone settings specifically, modifying the name server, NS records, or the delegation set,
They own your domain's resolution. Game over.
pretty much. They can point your domain anywhere they want. Redirect traffic, set up phishing sites, intercept email. It's a catastrophic failure and often completely preventable with strict MFA enforcement and applying the principle of least privilege to those powerful IAM actions.
So connecting it all up. The integrity of your entire global resilient DNS setup can be completely undermined by the weakest link. The permissions granted to and the security posture of your administrative IAM users. MFA and least privilege aren't optional for these critical actions.
They are absolutely mandatory table stakes.
Okay, we've routed the traffic globally with Route 53. Now let's talk about delivering the content efficiently and securely using CloudFront, Amazon's CDN. The sources position CloudFront as the true security perimeter for global apps.
That's right. And its effectiveness comes from its architecture, specifically its multi-tiered caching hierarchy. It's not just one layer of cache.
Right, you start with the edge locations, the POPs.
Yeah.
Hundreds of them, closest to the end users for the lowest possible latency.
Exactly. That's the first place CloudFront looks for requested content. If it finds it there, cache it serves it immediately with very low latency. But if it's not there, a cache miss.
It doesn't necessarily go straight back to the origin server, say, my ALB in Ust East 1.
Not usually, especially for content that's not super popular globally, but maybe popular regionally. Instead of every edge location independently fetching from the origin, the request often goes to the second tier, the regional edge caches, or RECs.
Okay, what's the role of these RECs? Are they just bigger caches?
They are bigger, yes, but their role is strategic. They sit between the globally distributed edge locations and your origin server. They do two main things. First, they consolidate cache misses from multiple edge locations within that geographic region. So if 10 users in different cities served by different edge locations all miss the cache for the same file, the REC might only have to fetch it from the origin once.
Reducing the load on the origin.
Massively. Second, they act as a protective shield. Because they sit closer to the origin and have larger caches, they improve the cache hit ratio for content that isn't requested frequently enough to stay hot in every single edge location. It ensures that the potentially long-haul request from the edge back to your origin traverses the optimized AWS backbone network as few times as possible.
Better performance, less origin load. Makes sense. Now, that security perimeter aspect, you said CloudFront must be treated that way. How do we enforce that?
This brings us to a crucial security mandate: Origin Access Control, OAC. This is a non-negotiable customer responsibility. You must configure OAC to ensure that your CloudFront distribution is the only entity allowed to access your origin content.
Okay, OAC. I know there used to be something called Origin Access Identity, OAI. How is OAC different and why is it mandatory now?
OAC is the modern, recommended, and much more secure mechanism. OAI was the older method, particularly for S3 origins, and it had some limitations. OAC is based on standard AWS IAM principles. When you enable OAC for an origin, like an S3 bucket or even an ELB or custom HTTP server,
What happens?
CloudFront creates a dedicated IAM service principal specifically for that CloudFront distribution. You then update the resource policy on your origin, like the S3 bucket policy or the security group rules for your ELB, to only allow access from that specific CloudFront service principal.
So the policy on the origin explicitly says only CloudFront distribution ID XYZ is allowed to talk to me.
Precisely. The direct implication is any request that tries to bypass CloudFront and hit your origin URL directly, maybe someone found the S3 bucket URL or the ALB's DNS name, will fail. It won't have the necessary IAM credentials associated with the CloudFront service principal, so the origin will deny the request based on its policy.
That guarantees all legitimate traffic must flow through the CloudFront edge.
Correct. Which means it must pass through any AWS web ACLs you've associated with the CloudFront distribution, and it benefits from the baseline DDoS protection of AWS Shield. You can't have a secure perimeter if traffic can just walk around it. OAC locks that down.
Got it. Now, encryption again. We talked about client to AOB, view to edge in CloudFront terms, and ALB to origin. What about the hop from the CloudFront edge location back to the origin?
Edge to origin encryption. Best practice, strongly recommended by the sources, is to configure CloudFront to always use HTTPS when communicating with your origin, even if the origin is another AWS service like an S3 bucket or an ALB within your VPC.
Even over the AWS private backbone.
Yes. While that backbone is highly secure, using HTTPS for the edge-to-origin connection provides defense in depth. It mitigates even remote theoretical risks of internal eavesdropping or man-in-the-middle issues and ensures data confidentiality for that entire path. You configure this in the CloudFront origin settings, setting the origin protocol policy to HTTPS only.
Okay. Beyond security, there's a big financial incentive to use CloudFront with AWS origins, isn't there?
Huge. A major cost optimization incentive. Data transfer out from AWS origin like S3 buckets, EC2 instances, or ELBs to CloudFront edge locations for an origin fetch is free.
Free data transfer out from AWS to CloudFront.
Correct. AWS doesn't charge you for the bytes transferred from your AWS origin to CloudFront when CloudFront is fetching content to serve to users. This makes it extremely cost-effective to put CloudFront in front of origins hosted within AWS, as you avoid potentially significant data transfer charges you'd incur if users hit the origin directly. It strongly reinforces the architectural pattern of using CloudFront as the front door.
Makes sense. Now, CloudFront isn't just about caching and delivery anymore. It has compute capabilities at the edge. Let's talk about the two options. Lambda at edge versus CloudFront functions. What's the difference?
They often get confused, but they serve very different use cases, primarily driven by complexity and latency sensitivity. Lambda at edge, L at E, is the more powerful, more flexible option. It lets you run Node.js or Python code in response to CloudFront events, viewer request response, origin request response.
So full Lambda function capabilities, but running globally.
Essentially, yes. It runs in a standard Lambda execution environment, just distributed globally near the CloudFront edge locations. Because it involves invoking a Lambda function, there's a bit more startup latency compared to CloudFront functions. This makes L at E suitable for more complex, latency-tolerant operations. Think sophisticated authentication logic, making external API calls, complex A/B testing decisions, dynamically rewriting large parts of a response body. Heavy lifting.
Okay, so L at E for the complex stuff. What about CloudFront functions?
CloudFront functions are the lightweight sprinters. They're designed for simple, extremely latency-sensitive tasks that need to run really, really fast. Think microseconds of execution time, not milliseconds like L at E.
Microseconds. How do they achieve that?
They run directly within the CloudFront Edge process itself, not in a separate Lambda container. They are JavaScript only and have much stricter limitations, lower CPU time, less memory, no network access, no file system access. They can only run on the viewer request and viewer response events, the phases closest to the user.
So what are they good for then?
Perfect for simple, high-volume manipulations like URL rewrites or redirects, normalizing HTTP headers like converting everything to lowercase, manipulating cache keys based on headers or cookies, or maybe adding basic security headers like HSTS. Things that need to happen instantly without adding any perceptible latency for the user.
So L at E for complex logic where a few milliseconds is okay. CloudFront functions for super fast, simple manipulations right at the edge.
That's the core distinction. Choose the right tool for the job based on complexity and latency requirements.
Okay, we've established CloudFront and ALB as that essential security perimeter, which means we need layers of defense there. Let's break down the DDoS protection strategy with Shield and WEF, keeping that shared responsibility model in mind.
Right, the layers start automatically. Every AWS customer gets AWS Shield Standard at no extra cost. This provides baseline protection against the most common volumetric network layer, layer 3, and transport layer 4 DDoS attacks. Think SYN floods, UDP reflection attacks.
And because that's protecting the underlying AWS infrastructure.
That falls squarely under AWS's responsibility. Security of the cloud. They manage the detection and mitigation of those common L3, L4 attacks automatically.
But what if you need more? Maybe you're a high-profile target, or you have very strict uptime requirements.
Then you'd look at subscribing to AWS Shield Advanced. This is a paid service offering much more sophisticated L3, L4 detection and mitigation. Crucially, it provides cost protection absorbing DDoS-related scaling charges on protected resources like CloudFront or ALBs. And, maybe most importantly, it gives you 24/7 access to the AWS DDoS response team, the DRT.
The DRT, actual humans you can talk to during a major attack.
Exactly. Experts who can help analyze the attack and fine-tune mitigations in real time. Shield Advanced is for organizations needing that higher level of protection and support.
Okay, so Shield Standard and Advanced handle the network and transport layers, but they don't really understand the application traffic itself, right? That's where WF comes in.
Precisely. AWS WAF operates purely at the application layer, layer 7. It's designed to protect against web application attacks that often look like legitimate traffic things like SQL injection, SQLi, cross-site scripting, XSS, malicious bots, scraping, etc.
And because WAF protection relies entirely on the rules we define.
It's firmly in the customer's court, security in the cloud. AWS provides the WAF service, but you are responsible for creating the web ACLs, configuring the rules, using AWS managed rules, custom rules, rate-based rules, and deciding how to handle matching requests. Allow, block, count, cap TCHA.
Now, the sources really emphasize that just turning on WAF isn't enough. Configuring it effectively against modern threats is the hard part. They mention a specific historical incident involving a Layer 7 DDoS attack that bypassed a seemingly reasonable WAF setup.
Yes, this is a critical lesson. The incident involved a sophisticated HTTP flood attack. The target had an ALB protected by AWS WAF, and they even had rate-based rules configured, but the attack still overwhelmed the application. Why?
The rate-based rule was too simple.
Exactly. It was configured to aggregate and count requests based only on the source IP address. So it might have said, block any single IP sending more than 1,000 requests per minute.
But the attack wasn't coming from one IP. It was a distributed botnet, maybe thousands of compromised machines, each sending requests at a low rate.
Precisely. Each individual bot stayed well below the per IP threshold. The wave rule, looking only at single IPs, saw nothing wrong. But collectively, the sheer volume of requests from all those distributed sources saturated the application servers. The simplistic single-dimension rule was completely ineffective against a distributed L7 attack.
So the failure wasn't WAF itself, but the customer's configuration of the wave rules.
A direct failure of configuration management, yes. It demonstrated that security rules need to be as sophisticated as the attacks they face. This leads to a clear mitigation mandate from the sources. You must implement a multidimensional defense strategy in your WAF.
Multidimensional, meaning don't just look at the IP address.
Right. Move beyond simple IP filtering. Your rate-based rules need to aggregate traffic based on multiple request characteristics combined. For example, aggregate based on the combination of source IP and the user agent string. Or maybe source IP and a specific cookie value. Or perhaps based on labels that NoBF applies after running a captcha or JavaScript challenge.
So you're building a more detailed fingerprint of the traffic source,
Yeah.
making it harder for bots to blend in just by using different IPs.
Exactly. This higher fidelity allows you to identify and limit or block genuinely abusive traffic patterns without inadvertently blocking large numbers of legitimate users who might happen to share an IP range, like from a corporate network or a mobile carrier. It's about turning WAF from a simple gatekeeper into more of a behavioral analysis engine.
Yeah, that makes a lot of sense. It's a necessary evolution. We also need to quickly revisit TLS handshake security. The sources mentioned vulnerabilities there, too.
Yes, specifically around cipher downgrade attacks. Analysis of some incidents trace the root cause back to organizations using older, less secure ELB security policies. These older policies might permit negotiation using weaker cipher suites or older TLS versions that are known to be vulnerable.
So again, a configuration issue leading to a security gap.
Absolutely, which is why continuous compliance monitoring of your TLS policies is mandatory. You need processes to ensure you're always using policies that enforce a minimum of TLS 1.2, and ideally policies that prioritize or mandate TLS 1.3.
And the ALB helps enforce this consistently.
Yes. The security policy you select on the listener dictates the allowed protocols and ciphers for the client connection. And importantly, the sources note that the ALB intelligently selects an appropriate back-end security policy for the ALB to target connection based on the front-end policy you chose, ensuring cryptographic best practices are maintained throughout the connection path, preventing those risky downgrade scenarios.
Okay, we've covered global routing, delivery, and security. But true operational excellence also means handling localized failures gracefully. Let's dig into some advanced AWS features for operational resilience, starting with zonal shift and ARC.
Right. Zonal shift is a powerful operational lever, tightly integrated with AWS Application Recovery Controller, or ARC. It's essentially a pre-provisioned emergency brake that lets you quickly shift traffic away from a single, potentially impaired availability zone, AZ.
When would you use this manually? Wouldn't normal health checks eventually take unhealthy instances out of rotation anyway?
They would eventually, but zonal shift is for situations where you might detect a problem at the zonal level before individual instances are clearly unhealthy. Maybe your monitoring shows a sudden spike in latency just for traffic going through AZA, or a rise in connection errors localized to that AZ even though the instance health checks are still passing.
So it suggests a deeper issue, maybe network problems within that AZ or something affecting the load balancer nodes there that the target level health checks aren't catching yet.
Exactly. Rather than waiting for the problem to worsen and potentially cascade, zonal shift gives you the control. With a simple ARC API call, you effectively tell Route 53 if using an alias record to the ALB, or the load balancer's internal DNS resolution to temporarily stop resolving the ALB's IP addresses associated with that specific impaired AZ.
So traffic just stops flowing to that AZ almost instantly.
Yes, it drains the traffic away from the suspect AZ, allowing the healthy AZs to pick up the load while you investigate the issue in the impaired zone without impacting users further. It's a proactive, contained failure mitigation tool.
And I imagine it's also useful for testing.
Absolutely essential for resilience testing. You can use zonal shift to deliberately simulate the loss of an AZ during a controlled test window to verify that your application and infrastructure in the remaining AZs can actually handle the increased load and function correctly. It proves your multi-AZ architecture really works under stress.
Okay, powerful tool. Let's pivot to some specific ALB attributes that give us finer-grained control over how the load balancer handles the HTTP traffic itself. The sources highlighted desync mitigation mode. What's that about?
HTTP desync attacks. They're a nasty class of web security vulnerability where an attacker crafts ambiguous HTTP requests that violate the standards, RFC 7230. The goal is to make the front-end load balancer interpret the request boundaries differently than the back-end server, potentially allowing the attacker to smuggle malicious requests past security controls.
Sounds tricky. How does the ALD protect against this?
The ALB has this desync mitigation mode attribute. The default setting is defensive. In this mode, the ALB actively analyzes incoming requests for compliance with HTTP standards.
What does it do if it finds a non-compliant, potentially dangerous request?
It classifies the threat level. If a request is deemed severe, meaning it has a high likelihood of causing a desync attack, the ALB blocks it outright, returns a 400 bad request error, closes the connection, and increments a specific metric. If the request is classified as merely ambiguous, less risky but still non-standard, the ALB might try to handle it in the safest possible way, but it still flags it.
And crucially, we get visibility into this.
Yes, that's key. The ALB publishes a CloudWatch metric called Desync Mitigation Mode Non-Compliant Request Count. You can monitor this metric to see if you're receiving these kinds of potentially harmful requests. Furthermore, the classification reason, ambiguous or severe, is logged in the ALB access logs for detailed analysis. It's a critical layer of protocol-level security.
Good to know. We also need to be careful about how client identity information is passed back, specifically those X-forwarded headers.
Especially the X-forwarded for header, which carries the original client IP address. The ALB needs to add the client IP to this header since it terminates the original connection. But how it does this is controlled by an attribute, routing.http.xff header processing.mode. The default is append,
Meaning it adds the client IP it sees to the end of any existing X-forwarded for header value that might have come from upstream proxies.
Correct. Other modes are preserve, trust the incoming header, don't modify or remove, strip any incoming header, and only add the IP the ALB sees. The sources advise caution here.
Why caution? Append seems reasonable.
Because the load balancer inherently trusts the incoming request. If there's an insecure proxy or maybe even a malicious client manipulating headers before the request hits your ALB, the X-forwarded for header arriving at the ALB might already contain spoofed IP addresses. If your application blindly trusts the first IP in that list, a common mistake, it could be misled about the true client origin. Setting the mode requires careful consideration of your entire request chain and where you establish trust.
Okay, so understand your upstream hops and configure accordingly. What about X-forwarded proto?
That one's usually more straightforward, but equally essential. Since the ALB terminates the client's TLS connection, if using HTTPS, the connection from the ALB to your backend target might be plain HTTP internally. The X-forwarded proto header, automatically added by the ALB, tells your backend application whether the original client connection was HTTP or HTTPS.
Which is critical for any application logic that depends on knowing if the user was secure, like generating correct absolute URLs or enforcing secure-only sections.
Exactly. Without it, the backend would be blind to the original connection's security status.
Let's talk performance and capacity.
Yeah.
ALBs scale automatically, which is great, but sometimes you get those massive sudden traffic spikes like a flash sale or a big announcement. Can that cold start scaling still cause issues?
It absolutely can. Automatic scaling takes a little time to react. If you suddenly go from very low traffic to extremely high traffic, the existing ALB nodes might get overwhelmed before new capacity spins up, leading to dropped connections. You'd see the rejected connection count metric spike. This is where load balancer capacity unit, LCU reservation, comes in.
LCU reservation sounds like pre-warming capacity.
That's exactly what it is. It allows you, typically for an additional cost, to reserve a guaranteed minimum amount of capacity, measured in LCUs, for your load balancer. This reserved capacity is provisioned upfront and distributed evenly across the AZs your ALB is enabled in.
So why pay extra for this?
To handle those predictable, massive, sudden spikes. If you know you're launching a Super Bowl ad or starting a major sales event at precisely 9:00 a.m., reserving LCUs ensures the ALB infrastructure is already scaled up and ready to handle that initial massive influx of traffic instantly, avoiding those cold start connection drops during the most critical moments. It's for ensuring performance during planned high-load events or sometimes during migrations.
And speaking of intelligent capacity and performance management, tell us about automatic target weights, ATW. You mentioned it works differently from standard health checks.
Yeah, ATW is a really neat self-healing feature operating at the target group level. Standard health checks are binary. Is the target healthy or unhealthy based on a specific check? ATW goes further. It continuously monitors the performance of healthy targets looking for anomalies.
Anomalies like?
Like a specific target suddenly starting to generate significantly more 5-to-X errors than its peers, or experiencing higher connection failure rates, or maybe having unusually high latency, even though it's still passing the basic health check endpoint test.
So it detects subtle degradation, not just outright failure.
Exactly. It uses anomaly detection algorithms. And here's the clever part. If you're using the weighted random routing algorithm for that target group, ATW can automatically react to detected anomalies.
How does it react?
It dynamically and temporarily reduces the weight assigned to the poorly performing target, meaning the ALB sends less traffic to it. It adjusts this weight down gradually, checking every 5 seconds. This gives the struggling target a chance to recover without being hammered by its full share of the load, while the healthier targets pick up the slack.
That sounds like automated gradual degradation handling.
It is. It's a key feature for building more resilient, self-healing applications, allowing the system to automatically compensate for gray failures or temporary performance dips without manual intervention or waiting for a target to fail its health check completely.
Brilliant. Okay, finally, none of this matters if we can't see what's going on. Visibility and auditing.
Absolutely critical. We rely on 3 main pillars here, according to the sources. First, access logs. These are incredibly detailed logs of every single request processed by the ALB.
What kind of detail are we talking about?
Time received, client IP, latencies, target processing time, request time, the full request path and method, the response codes sent back by the target and by the ELB itself. They're typically delivered to an S3 bucket every 5 minutes or so. Crucially, for security auditing, they also include details like the TLS cipher and protocol negotiated with the client, the ARN of the specific TLS certificate used, and, as we mentioned, that desync mitigation mode classification.
Okay, that's request level detail. What's the second pillar?
Connection logs. These operate at a slightly different level, capturing metadata about the TCP connection attempt itself rather than the individual HTTP requests within it.
So things like
Client IP import, target IP import, connection duration, and importantly, things like TLS handshake latency. If you're using mutual TLS, MTLS, where the client also presents a certificate, the connection logs can capture information about that client certificate validation process. They give you visibility into the connection establishment phase.
access logs for requests, connection logs for connections. And the third pillar is the real-time view.
CloudWatch metrics. The ALB publishes a wealth of metrics every 60 seconds, providing near real-time visibility into performance and health. These cover both the load balancer itself and the individual target groups.
Key metrics to watch.
Things like healthy host count and unhealthy host count are fundamental. HTTP code ELB5XX count tells you if the load balancer itself is having issues talking to targets. HTTP code target 5XX count tells you if your application targets are throwing errors. Target response time tracks application latency. Rejected connection count warns you about capacity issues. Low reputation packets dropped shows if Shield is actively dropping known bad traffic. These metrics are essential for building dashboards, setting alarms, and triggering automated responses.
Wow. That was an incredibly comprehensive tour through the layers of controls, security, and visibility needed to manage a global application on AWS. It really drives home that high availability and security aren't magic. They're the result of thousands of small, deliberate, and correctly configured details.
Absolutely. Getting these configurations right is paramount. #tagoutro. So let's try to synthesize the absolute core architectural mandates for you, the listener, from this deep dive. These AWS Global Services, ALB, Route 53, CloudFront, they are incredibly powerful, immensely scalable, but they absolutely operate under that unforgiving logic. Garbage in, garbage out when it comes to your configuration.
Yeah, we saw that painful lesson with Route 53, the absolute mandate for static stability in disaster recovery. You simply cannot build a reliable recovery plan that depends on calling a control plane API, like change resource record sets, during the crisis itself. Pre-provision your failover paths, use health checks, use ARC routing controls, rely only on the globally resilient data plane when things go wrong.
Architecturally, you must treat CloudFront as the single mandatory security perimeter. No excuses. That means rigorously enforcing origin access control, OAC. Lock down your origin so that literally the only way traffic can reach them is by coming through your CloudFront distribution. That ensures every request gets scrutinized by your WEF rules and benefits from Shield protection.
And the defense game at Layer 7 has changed. The sources make it clear. Moving to multidimensional WEF defenses isn't optional anymore. Simple IP-based rate limiting just doesn't cut it against modern distributed botnets. You have to configure WEF to look at multiple factors: IP plus user agent, IP plus headers, maybe use challenges to build that behavioral profile and block the bad actors without impacting legitimate users. Your WEF needs to be smarter.
And tying it all back to that central theme, the shared responsibility model, it echoes through everything we discussed. AWS provides this incredibly secure and resilient global cloud infrastructure security of the cloud, But you, the customer, are entirely responsible for configuring security in the cloud.
That means.
It means rigorous MFA enforcement on critical IAM users, especially those controlling DNS. It means migrating off old TLS 1.0, 1.1 policies immediately and using modern TLS 1.3 policies. It means paying attention to those granular operational controls. AWS provides things like desync mitigation mode for protocol security or automatic target weights for self-healing and actually leveraging them to build operational maturity.
So the takeaway is, the most sophisticated, globally distributed delivery system on the planet is only as resilient as its weakest configuration point, and only as recoverable as the mechanism that doesn't need an API call when everything is burning down.
Exactly. And given the sheer complexity and evasiveness of modern Layer 7 attacks, the question really isn't if your simplistic, single-dimension W-life rate-limiting rule will eventually fail you. The question is when. And when it does, will your monitoring, your CloudWatch metrics, your detailed access logs showing things like desync classifications be granular enough and tied into automation tightly enough to trigger the right programmatic response? That's the challenge. Go explore configuring that truly resilient self-healing architecture today.